Dear friends, welcome to Turbo Missions class of session 7 of module 1. I am Dr. Rudresh from Government Engineering College, Krishnarajpete. Let us see some few more informations in this session about a turbo machine process and a turbo machine system. We have an expansion process, efficiency of expansion in turbine, total to total efficiency and total to static efficiency, polytropic efficiency in expansion, read factor in expansion, compression process, total to total efficiency and static to static efficiency, polytropic efficiency in compression. So one important the fact which I am bringing in front of you is that see expansion process and the compression process are part of a turbo machine system. So when you consider these particular operations or when you consider these particular process, what changes are going to occur with respect to a particular fluid? At the same time, how you can evaluate the performance of a turbo machine during that condition. So this is very important. Therefore, the beauty of a turbo machine always lies with this kind of fluids also. We need not stick on our particular discussion only to the hydraulic fluids or only to some other type of the fluids. We need to talk about in general how exactly, suppose if the fluid is a low tensor fluid, how it is possible to have the overall performance of a respective turbo machines. So let us see in this system in this particular session, right? So what are the things that we need to consider? So next is, let us talk about an expansion process. Now we are all seeing enthalpy entropy diagram in this case. So we know that the efficiency of a turbine is always defined as the ratio of actual total work out to the total work output to the ideal work output for the response ratio. Yes or no? If you want to define an efficiency in case of a turbo machine system, there are two important concepts we have to keep in mind. Just now in the previous sessions, we discussed about a static state as well as a stagnation state. Total state as well as a static state. Yes or no? Therefore, without considering the static state and the stagnation state, it is not possible to evaluate the performance of a respective turbo machines. Therefore, if you want to define a efficiency of a turbo machines, so there are two important efficiencies that we have to consider in expansion process. One is the total to total efficiency, the other one is the total to static efficiency. In the beginning of the process itself, right, in the beginning of the stagnation related issues, we talked about a static state. Static state is the initial state of a stagnation states. Yes or no? So for that purpose, we have to think about how we can define this particular expansion process considering these two efficiencies. Now let us see the figure. It's an ideal and actual expansion for a turbine system. So here we have got the different pressure systems. One is P1 is one static state, P2 is another static pressure. Between the two states, 1 and 2. Okay, P01 is the one stagnation pressure, P02 is the another stagnation pressure with respect to two stagnation states 1 and 2, that is 01 and 02 respectively. If you see here, we have got an isentropic change where the entropy remains constant. Okay, here also when you go to the stagnation state 2, here also we are having an isentropic entropy. Okay, so the drop in enthalpy or the drop in temperature, drop in enthalpy or a drop in temperature with respect to the static state, with respect to stagnation state. Both the systems are available at this particular stage. And we have got the expansion process here also, right? So when you say this, what is the actual work done and what is the isentropic work done? That also we have specified in this particular figure itself. Okay, next is, when you see this particular process, I will take one efficiency, total to total efficiency. We know that here we have got an isentropic work done, actual work done. There are two types of works which are available in this particular TS diagram. If I want to define a total to total efficiency, this total to total efficiency is only with respect to stagnation states, total to total. Therefore, it is the ratio of the actual work output to the ideal work output if the isentropic expansion takes place from inlet stagnation state 01 to exit stagnation state 02 dash. It's very important concept because we are measuring only with respect to stagnation states, from that is the inlet stagnation state to the outlet stagnation state. So that's why it is called a total to total efficiency. Therefore, total to total efficiency is equal to actual work output from the system to the ideal work output from the stagnation ends. So mathematically, if I want to put this in terms of enthalpy equation, eta T suffix T is equal to H naught 1. This is very, very important. Stagnation, initial stagnation condition H naught 1, final stagnation condition is H naught 2. This is very, very important. Okay. Therefore, this is what? Actual H naught 1 and H naught 2. This is the actual one. This can be taken as the actual enthalpy drop. H naught 1 minus H naught 2 divided by H naught 1 minus H naught 2 dash. This can be taken to be the ideal one or an isentropic enthalpy drop in a system. That is equal to T naught 1 minus T naught 2 divided by T naught 1 minus T naught 2 dash. Right. So this particular situation is there, that means the total stagnation conditions at state 1 to the total stagnation conditions at the second state. So that will define what is called as total to total efficiency. Actual work at the initial stagnation state, actual work at the ideal stagnation states, right? This is very, very important. Next, I am talking about total to static efficiency. It's the ratio of actual total work output to the ideal work output if the isentropic expansion takes place from inlet stagnation state 0, 1 to exit static state 2 dash. You just see this. In this particular figure, we have say inlet stagnation state 0, 1. 0, 2 is there, outlet stagnation state. Okay, so this is actual what we are talking about, right? So suppose if you consider this particular 2, this is also very, very important state in this case. Okay, so next is, so when you consider from 0, 1 to 2 dash, 2 dash is nothing but it's an isentropic point. At 2 dash, if you consider this particular isentropic point, so this is very, very important. Exit static state of state P2. This is very, very important. Therefore, H naught 1 minus H naught 2 divided by H naught 1 minus H2 dash, that is the static condition has to be considered for this particular stage, because we are defining total to static efficiency. Therefore, total to static efficiency is equal to T naught 1 minus T naught 2 divided by T naught 1 minus T2 dash. So if you define the polytropic efficiency in expansion, so we are talking about a temperature entropy diagram here. And what is the isentropic temperature drop and the actual enthalpy drop also we have talked about in this case, right? If you see this polytropic efficiency, it's the ratio of actual enthalpy drop to the isentropic enthalpy drop. Okay, so if you talk about this polytropic efficiency, eta P is equal to dH by dH dash. dH is nothing but it is the actual enthalpy drop, okay, which is carrying between these particular states which is available. So P and P minus dP, right? There are two states are available. P is the initial state, P minus dP the final state, right? At this particular points, what actually the enthalpy drop that took place, right? So that actual enthalpy drop to with respect to those two states, what actually the isentropic enthalpy drop has been takes place, right? So therefore, the polytropic efficiency is equal to the ratio of actual enthalpy drop to the ideal enthalpy drop, we can say, that is the isentropic enthalpy drop. Now when you see this compression process, now you are all seeing the enthalpy or a temperature entropy diagram in this case. So with usual state conditions P1, P2 are the two static conditions, static pressures P01 and P02 are the two stagnation and the pressure conditions, and the representation of the compression process has been done between the static states 1 and 2 and between 0, 1 to 0, 2 between the two stagnation states. Therefore, total to total efficiency which we have to define for a compression process also. When we are talking about the compression process, there are two efficiencies which we have to consider for the evaluation. One is total to total efficiency, static to static efficiency. So now I am talking about total to total efficiency. It is the ratio of ideal work between the stagnation states to the actual work. Okay. Therefore, total to total efficiency, it is the reverse of total to total efficiency of an expansion process. That's all. So ideal work output between the stagnation states to the actual work output. Therefore, when you are defining this particular thing, H02 dash minus H01 divided by H02 minus H01. Very, very important concept. You just see this. Even the process will be reversed here also. That's why. Once when you see the overall evaluation in terms of expansion process, the reverse will be the compression process. Therefore, T02 dash minus T01 divided by T02 minus T01. This is very important concept. See, so when we are defining this particular issues, we have two particular work done. One is isentropic work done and the other one is actual work done. Isentropic work done is nothing but it is an ideal work done. Okay, so if you rate this total to total efficiencies, which is from the total stagnation state T02 dash to T01. Yes or no? This is between the stagnation states, right? So actual work output. So when you see this actual work output, T02 is available with respect to that. So we are having, so from T02, so what is the total, what is the difference, right? So up to T01, that is the total difference with respect to stagnation states. So H02 minus H01 or T02 minus T01, anything you can take, right? So that defines the total to total efficiency in a compression process. Secondly, we have a static to static efficiency. If the efficiency is used on the static states, then it is called as a static to static efficiency. Therefore, here we have started from T2 dash minus T1. This is nothing but, see, isentropic drop. Okay, and T2 minus T1, this is with respect to purely static conditions. Yes or no? That means T2, T1 are the two static conditions. We are defining only with respect to static states only. That's why the efficiency is called static to static efficiency. Now, if you see the polytropic efficiency in a compression, so we know that the polytropic efficiency is very important both for compression process as well as an expansion process. How do you define this polytropic efficiency for a compression process? Similarly, it is the reverse of an expansion process. It is defined as the ratio of isentropic temperature rise to the actual temperature rise in the compression system. Right? Yes or no? Therefore, so when you see the polytropic efficiency for an expansion process is dt by dt dash. That is actual by isentropic. But in case of a compression process, polytropic efficiency is equal to dt dash by dt. So this particular variations are there, you know. So all are very important. How the fluid has been compressed from one particular state to another particular state. How the fluid is going to expand from one particular state to another particular state. Based on these particular expansions as well as the compression of the fluid through the action of a turbo machines, we can define what is called as the efficiencies in a turbo machine systems. Dear friends, so far we discussed about the different efficiencies which are available related to a compression as well as the expansion process of a particular turbine systems, right, or a particular turbo machine systems where the fluid is very lighter in nature, like the air as one of the fluid. There we can have the pure expansion as well as the pure compression of the respective process. Under that situation, totally we can define what is the meaning of a static state and what is the meaning of a stagnation state. With respect to static state as well as the stagnation state, we have to define the efficiencies. Therefore, total to total efficiency is available, total to static efficiency is available with respect to an expansion process. Whereas, when a compression process is concerned, it is purely total to total compression process, that means the efficiencies, and static to static efficiency that we have to consider for the respective compression process. Therefore, polytropic efficiency is also one of the important parameter which is used to characterize the turbo machines, right, both in expansion as well as compression process. Therefore, this thermodynamic efficiencies are very important in defining the thermal behavior of the fluid within the action of a turbo machines. Okay friends, in this session we discussed some efficiencies related to thermal fields, right, so which are closely related to the expansion as well as a compression process in case of a turbine turbo machine systems. Okay, thank you.